Hi, welcome to our first review session for AP Statistics. This is our review number 1. And this is analyzing one variable data. So we're talking about, what do we do with one variable data? How do we describe data? You're going to be given graphs or data, and you have to describe things like, what is the shape? What's the center? What's the spread? Well, what does all that mean? Let's talk about shape, center, and spread. Shape, center, and spread. Now, shape, we're talking about, is it roughly symmetric? You know, do you ever say anything's perfectly symmetric? No, but you might say it's roughly symmetric. So don't use the term normal unless you're told it's normal, all right? Don't say this shape is normal. You don't know it's normal unless you're told it's normal, okay? So it's roughly symmetric, or maybe it's skewed. Maybe it's, was that left skewed or right skewed? Ooh, it's skewed left. So it's always in the direction of the tail. Okay, so it's skewed left. And then you might have things that are skewed right. And once in a while, you'll have these weird ones like, hey, it's got 2 humps. It's like a camel. Or maybe it has 3 humps. Sometimes you have bimodal. There's lots of different distributions. If you don't know the name of the distribution, don't try to come up with something. Just say, just throw out what you see. All right, well, I noticed that the tail is going to the right. Okay, you didn't say skewed right, but there might be a stats reader saying, okay, I buy that. He meant skewed right. He knows what he's talking about. As long as you describe the shape when you're given distribution, you're good. Outliers. Outliers. That's pretty self-explanatory, but outliers are going to be there. If you see them, you got to point them out. What is the center? Typically, the center is things like the mean or the median. If you're given a set of data, it depends on what the data looks like. If it's symmetric, mean is perfectly fine. If it's skewed, though, you want to use the median, because remember, the mean is really is going to be pulled by the skewness, by those outliers. So the center, I would say, use the mean if symmetric. I would say use the mean or median if skewed. And as far as the spread goes, typically the spread is things like standard deviation. You might remember IQR. Oh my gosh, what's IQR? It's been a long time. Interquartile range, right? IQR, standard deviation. And again, the same rules apply, all right? What's gonna be thrown out more if it's skewed? The standard deviation will be affected if it's skewed. So if you have IQR, you want to use that if it's skewed. Otherwise, use the standard deviation if it's symmetric. So to summarize, if a question says describe the data, you need to cover those things, all right? You need to talk about shape, outlier, center, spread. There's an acronym called SOX. I think we used, we used that way back in the unit 1, but if you don't remember it, now's the time to think about, hey, these silly little acronyms, there's a place for them. Remember your socks, always wear your socks. I'm wearing my socks, and they're really colorful. People buy me weird, quirky socks, so I just wear them because I don't care. All right, any questions on that? I'm gonna look ahead here. And I just realized I went a little bit ahead of myself because I'm looking at the rest of the packet and it talks a little bit about more things on there. So there's examples of shapes, symmetric, roughly symmetric. I already kind of went over this, but hey, something like that. unimodal, bimodal. Bimodal would be like that. Skewed left. And skewed right. And then evenly distributed, another way that might be said is uniform. I don't know why I said evenly distribution, but uniform is the actual technical term for that. And that would be like this. Now, I don't know what data looks uniform, but most of the time it doesn't. But there is once in a while it looks like that. That's going to be that. And then again, like I said, don't assume that it's going to be normal. Okay, if it looks symmetric, it's not normal unless you're told it's normal. Now you can say it might resemble approximately normal. That's okay. But if you throw out the word normal, well, someone's going to say, no, you're not right. So the thing is if you say wrong information, they're going to mark you wrong no matter what. I've been pretty lenient on your free response just because it's hard to do this right now with you being home and everything like that. I understand. But I'm telling you, the people that score this stuff are not as lenient as I am. And when I get people in person next year, I won't be as lenient as I was this year. So you got off easy this year with your free responses. But approximately normal is okay if it looks symmetric, but do never say normal. Okay. I went over the center already. So again, mean is ideal for measure a center that's evenly distributed or roughly symmetric. So what the heck? Oh, goodness. This recording is not going to look very nice. Can I edit that out? So the mean is not going to be ideal for, if it's symmetric or whatever, you can use mean. Otherwise, if it's median, you're going to say, if it's got a skew or anything like that, use median. Because remember, in a distribution, if you have a skewness, the median will be closer to the actual center than the mean. Mean will always be to the right of the median if it's skewed right, and it'll always be to the left of the median if it's skewed left. So that's just how that works. Oh, and that's right here. So if it's left skewed, the mean is less than the median. And if it's right skewed, the mean is greater than the median. Don't assume that. Don't assume that if a distribution is skewed left, that a given mean is less than a median, or a distribution is skewed to the right. It usually is the case, but you have to kind of really read the question to see if there's anything that's not the situation like that. All right, let's go over the spread part. Spread. Spread your wings and fly. All right, the spread. We're talking about standard deviation, variance, interquartile range, and range. Now, we don't use the range very often here, but I will say be very careful on using the range, because trying to say the difference between the maximum and the minimum value, what does that mean? You know, it depends on the problem, but use sparingly. If you have outliers in there, don't use it, okay? Because if you have data like this, and then you have this outlier on there, the range doesn't mean anything. Most of your data is here, right? So if you're gonna use range, throw out the outliers first. But I would recommend not using range. And instead, my guess is if you're going to describe the spread, best thing to use interquartile range, because that's resistant to outliers. I mean, even if you have skewed data or uniform or symmetric data, interquartile range is still okay to use. But you're only going to use standard deviation when it's not when you don't have skewed or major outliers. Okay, that's kind of, and remember what standard deviation represents is the typical distance from the mean. Okay, so it doesn't mean like this specific point is this far away from the mean. It's like on average, your typical point is your standard deviation from a mean. And standard deviation, by the way, is measured in whatever units the mean is measured in. Now, we don't really go through and talk about variance, and I think I brought it up maybe a couple times, but variance is basically the standard deviation squared. So when you see, the reason we do variance is because in another review session we do, you'll see we have to square the standard deviation when we're combining sets of data. So that's the reason variance is useful. But when you're trying to describe spread, variance is the last of resorts that I would use. First thing I would say is interquartile range. Then maybe if it's symmetric, I do standard deviation. And I really don't hesitate to use range, and I never use variance, to be honest with you. That's just not there. Okay. Next on our list is outliers. We have to know how to calculate outliers. We have to know how to calculate outliers. Outliers on your, if you get a box plot, and if you use the box plot that has the outliers on there, and when we do some multiple choice problems and free response, I can refresh you on how to do that. But I'm going to be honest with you, most of the graphs on the exam are drawn for you. So you really don't need to be entering a lot of data in your calculator. A lot of it's just interpreting it. If you do that box plot like this and you have an outlier, well, that's a surefire way to be an outlier, right? But most of the time, we're not going to need that. Most of the time, you're going to use what we call the 1.5 IQR rule. And if you don't remember it, it's the outliers, anything below it's going to be less than Q1. Q1 is this here, by the way. Q3 is here. So Q1 minus 1.5 IQR. And the IQR is the difference between the quartiles. And if you're not given that, then you'll have to go in your stat menu to get those and go to your stat calc 1. Anything less than that is an outlier. Also, anything greater than, sorry, my pen is acting up, Q3 plus 1.5 IQR. So think about IQR times 1.5. Think about this, now that we've learned confidence intervals, think about this as being your margin of error. Okay. You know, I don't really make that connection when I teach it to you guys because we haven't learned about margin of error, but anything above, you know, the middle 50% of your data is in here, right? So if you have your margin of error, anything above that margin of error is an outlier. Anything below that margin of error is an outlier. All right. Let's talk about transforming data. What does it mean to like combine data, transform it, move it up and down, increase the height of it or whatever? So basically, if you have a set of data, if you add the same number to each element in the data, so let's say you have like, I don't know, we'll say 2, 3, 4, 5. If I add a constant to all those, so like, let's say 6. Well, that's going to change everything by 6, right? It's going to change the mean by 6. It's going to change the median by 6. But what's not going to change is the standard deviation and the IQR. Because remember, this is the spread. And the spread doesn't change. Spread doesn't change. If I shift everything right or left, spread doesn't change when you shift. So if you add or subtract every location, the Q3 will be higher or lower, the Q1 will be higher or lower, but because they'll be higher or lower the same amount, that IQR will be the same. Standard deviation will be the same. Multiplying, that's a different story, because what multiplying does is going to either decrease or increase the spread. So that will, multiplying will do everything, right? It'll take each element, and it'll increase the mean by that much. If you multiply it, it'll increase the median and the spread, because if you multiply every number, if it's multiplied by a number greater than 1, it's going to be a larger spread. If it's multiplied by a number smaller than 1, it's going to be a smaller spread. So that will increase the spread depending on what you multiply it by, okay? It'll actually multiply the variance by k-squared, but you know, that's not really super important right now. Just know that multiplying numbers will increase or decrease the spread as well as the location. Now, what's never going to change is z-scores. A z-score, however many data are above, however many standard deviations above or below the mean, that's a set number, okay? Z-scores will never be affected by multiplying or adding, because a z-score is always going to be centered around 0. It's always going to have a standard deviation of 1. So remember, a z-score of 1 is 1 standard deviation above the mean. A z-score of -2 is 2 standard deviations below the mean. And a z-score it'll still, relative to wherever the mean was, it's still going to be the same value, okay? So that's the real quick thing on transforming data. Talk about graphical displays. How to read, interpret, and construct from one variable data: stem plots, dot plots, histograms. The preferred data that I like to use from the calculator is a box plot. Those are easy, right? That you can just go to the stat calc, and you can go to your stat plot from your calculator and get a box plot, and I'll show you outliers. Histograms and stem plots are generally going to be drawn for you. You have to know how to interpret those. So stem plots, you remember, are going to look like this. Typically, it'll have like a number here, and usually there'll be a key saying what the numbers are. So like you'll have several dots or several numbers representing different sets of data, and a lot of times there'll be basically a bar graph sideways, okay? So stem plots look like that. Dot plots are the most basic of them. You see a lot of dot plots in some of the lessons we do, because it's like, oh, okay, well, you know, we have this many here. I'm just throwing out some random dot plots, but knowing what a dot plot looks like and how to interpret and kind of analyze that data and make some sense out of it, that's important too. Histograms talk about, there's 2 different types of histograms. One is frequency and one's relative frequency. So with histograms, it's like a bar graph, but you know, it's between certain intervals. So that interval is going to be the same width. And if it's percent, it's a relative frequency. If it's counts, it's just straight up frequency. So that just depends on what it is. And remember, that's going to be a range of values. So it might be like 5, 10, 15, and that width would be between 5 and 10, 10 and 15, 15 and 20. We're not going to change widths up in histograms. What we want to do from these, and we don't typically, box plots, of course, are going to look like this. And from those, you're going to have your min, your Q1, your median, your Q3, and your max. Unless you have an outlier, that might not show up in the whisker there for the box, but that's what the box plot looks like. Bar graphs are going to be either side by side or segmented We don't see a lot of bar graphs in our stuff because a lot of times we stick with histograms, but a segmented bar graph basically adds to 100%. So you might have different categories of data all adding to 100%. And so let me show you what that looks like because it's been a little while since you've probably seen one. A segmented bar graph might be color coded or whatnot, and it's going to have different shaded portions of it. So it might be there, you might have this portion of it represent this percent and that percent. But the whole purpose of a segmented bar graph is to kind of show the distribution of a variable. And so that's going to be adds to 100 right there. What we want to be able to do is not necessarily get exact, but get approximate means, medians, quartiles, outliers from these graphs. And as you come into the some of the multiple choice questions, you'll get into some of those problems that we'll go over how to do. You want to be able to compare graphs from data sets. A lot of times on the investigative task, you might be asked to construct a graphical display. So if you do have to draw a graph, pretty much guaranteed it's going to be on the investigative task if you have to draw one, okay? All right, that was quite a bit on that. So let me kind of just finish up with technology piece. When you're given a list of data without any, if you're given just a list of data, use your stat list to do one variable stats. You know, when you throw out your calculator, just know how to access your stat menu, know how to put in data. You're going to be given a school calculator. You can bring your own, but you know, you don't have to. I would just prefer you to use the yellow calculator I give you. Unfortunately, there are way better calculators than the TI-84s, but this is currently the only one allowed. So remember, when you're entering data in there, you can go to L1, you can enter your numbers in there. Then you can just click Stat Calc and go to one variable stats and make sure whatever list you put it in there, and you go down to calculate, and it'll give you all the stuff. It'll give you things like the mean, the standard deviation, all right? It'll give you the mean. It'll give you the standard deviation. Usually there's two standard deviations, right? There's that's the sample standard deviation. And then there's this, population standard deviation. Never use that unless you're specifically told that is everybody in the population. This is the one that you go to if you need to use one. And then you have your 5-number summary at the bottom. You have your N, how many you have. And then your Q1, your min, your Q median. If you scroll down, you see all that stuff. So you can get all that information from there to help you analyze the data. Okay, I know this is a lot. I appreciate you staying with me here. Going on to the next part is talking about normal curves, normal distributions, Z-scores, all that. So a Z-score is a standardized score, and it's always centered around 0. And the Z-score tells us how many standard deviations above or below the mean, right? So standard deviations above or below the mean is your Z-score. So if it's a negative, it's below. If it's a positive, it's above. So in this case here, this would be, if I wanted to know, hey, I got a set of data. It's got a mean of 10 and a standard deviation of 2. What's the probability of a number being greater than 12? First, we got to get the Z-score if you're doing it by hand. And you would do 12 minus 10 over 2. So it's always going to be this formula here. And we use these scores to kind of analyze where that point is in the data, but also we can use the Z-score to look up in the table A what the probability of something being below that number is. I prefer to use NormalCDF, but you have table A as an option if you want to stick with Z-scores. Now, how do we calculate that probability? How do I calculate, hey, what's the probability that Z is above 1? I like NormalCDF. Now, what I typically do is, I'll go to NormalCDF and I'll say, I'll do second vars. NormalCDF is number 2. Let me try that again, second vars. NormalCDF is number 2. And my lower, since it wants to be above, is going to be 1. My upper, I wrote 10,000, but obviously you can do 1E99. Your goal is to have the highest number possible when it's going above it. If it's a Z-score, we keep the mean at 0 and the standard deviation at 1. If the data is different, then we're going to use something else. So in this case here, notice that if I use 0 and 1, that's going to give me 0.1586. The probability of it being above 1 is going to be about 16%. Well, I could also do second vars, NormalCDF. If I know that that X value is 12, and my mean was 10, and my standard deviation was 2, remember, NormalCDF does not have to be using Z-scores. It can be using the same original data. As long as your mean and standard deviation reflect the same ones as what you use to calculate your Z-score, you'll get that same probability. So just kind of notice the difference between those two. Those are basically the same thing. One thing that might get you doc points if you just write NormalCDF in the number and put the numbers without context. So what I would suggest doing is put a sketch out there. When we did normal curve stuff, you might remember I said, hey, draw a sketch, shade above or below it, depending on what you're asked to accompany your work. That way, a reader knows you're knowing how to actually interpret the data, not just crunch numbers in a calculator. Okay. A lot of times, people tend to be old-fashioned and say you need to look at a table and say the probability this is less than that from a table. And I don't like to do that. I just kind of use the calculator for that. So use the given point, the standard deviation and mean. I don't necessarily need to see a Z-score if I'm looking at it. You can stick with this, but you do need to accompany it with a diagram when you're showing that shaded region. Holy cow. So are there any questions on that? And again, that 10,000 could be just 1E99, which is infinity, highest number possible. All right, a little bit more here. Now, if you're going lower, or if you're going between values, then you can use NormalCDF lower and upper. So for instance, if I wanted to do, what's the probability something's going to be between, if the mean is 10 and the standard deviation is 2, what's the probability X is between, let's say, 8 and 11? Well, I can do that, but this is going to be my lower, and this is going to be my upper. And so you can kind of test that in there, and you can say, all right, sketch it out. It'll look something like this. Remember, the standard deviation is 2, so it's counting up by 2s, 12, 14, 8, 6, and 8 and 11. Well, that's going to be somewhere here, right? 8. So you can kind of eyeball that and say, oh, that looks like it's going to be, I don't know, maybe close to 50%. But to get that exact amount, that's a NormalCDF. And what did I say, about 50%? A little bit over 50%, so like 53%. But that's the idea, right? Visualize where that's going to be on the NormalCDF, and always try to accompany a sketch if you're just doing a straight normal calculation. Now, if you're doing a whole bunch of other stuff like, significance tests and whatever, and that incorporate normal curves, You don't got to sketch that stuff. But if it's just like, hey, what's the probability it's going to be above this number, whatever, make a sketch of it if you can, okay? You might be asked to do percentiles. For percentiles, that's going to be involving using a combination of the Z-score or inverse norm to help get percentiles. So what is a percentile? It's basically, if you're in the 90th percentile, that means you scored above 90% of the people that took whatever test or whatever thing you accomplished, okay? That's what a percentile is. So I like inverse norm. So if you want to know, hey, what's the 75th percentile when you have that mean of 10 and standard deviation of 2, you can use the inverse norm command. So I'll do that here real quick, show you. So inverse norm, second vars, is the third option. And it's always going to be the area below. Now, you won't have, my handheld calculators do not have this fancy left, center, right. It's pretty cool. I wish if I maybe update the software, they will, but I don't. Actually, maybe I will try to update them, but I don't think all of them can be updated. So that's typically going to be the area below the curve. And you just put the mean and standard deviation. And there, that is the percentile. So, or that is the location. So the 75th percentile is about 11.34, 11.35. That's what the 75th percentile is. Here's another example here. Given a set of data with a mean of 10, a standard deviation of 2, 65% of the data is greater than what number? Well, in this case here, if it's a greater, then you have to subtract that from 1, because think about what this means. 65% is greater means that I want to know what the 35th percentile is. 65% is up here, but inverse norm only goes to the left, right? So you got to subtract from 1. So 1 minus 0.65 is 0.35. So that's what you want to throw in there if you're going a greater than. So anytime it's greater, subtract from 1, and then do your inverse norm. As with Z-score, it's not a bad idea to sketch a normal curve and show that shaded region. So this is what you want to show on the shaded region, not what I just did here. But you want to interpret in your calculator that 35%, because that's what you're going to use to get it. You can use table A, but you still got to subtract from 1. So if you get the Z-score and use table A, that's an option as well. We are almost done with the notes. I've taken a lot of your time. So this is the last thing, and then you can work on the multiple choice questions, okay? So talking about kind of finishing out, it's possible to determine outliers using the 1.5 IQR from a normal curve. You can calculate the first and third quartiles by getting the 25th or 75th percentile and using inverse norm. So hold on. So what does that mean? So if I want to know what the actual third and first quartile is, let's say the mean was 10 again, and the standard deviation was 2. I'll just kind of throw this out here. If I want to know, hey, what's Q1? That's going to be at the 25th percentile. And then Q3 is going to be at the 75th percentile. So you would do the inverse norm with those numbers. And just do 0.25. And this number represents your 25th percentile by 8.65. And then the 75th percentile is here. So your IQR would just be 11.634 minus 8.65. 11.35, not 111, just 11. Okay, that's weird. So your IQR is approximately about 2.7. So you can use your 1.5 IQR rule to figure out if there's outliers if you had a bigger set of data to work. That's a lot of information for one little class period, but you'll have some multiple choice questions. So this one is this is the biggest of the multiple choice questions. So just kind of give you a heads up here. I'll get these started copying these this afternoon and getting these ready for you. Message me or stay on later if you want to kind of work out how to get these in your hand. I want to get not just the first packet, but I want to get all of them with you so we don't have to keep doing this every time. So hopefully you got some good information. I'm going to stop the recording and I'll share this recording so that way